Good evening, all. I welcome you all for the day 3, session 4 of a NAMPED sponsored short-term online course on power electronics converters applications in microgrid and vehicular technology from 20th July to 24th July 2022, organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela, Odisha, India. It's my privilege to read the biodata of Dr. Venkat N. Jakka. Dr. Venkat N. Jakka received a PhD in electrical engineering from IIT Bombay in the year 2017. He applied for 3 Indian patents and 1 US patent, out of which 1 US patent and 1 Indian patent are granted. He completed his BTech degree in electrical engineering from Indira Gandhi Institute of Technology, Saran, and MTech degree in power electronics specialization from National Institute of Technology, Calicut in 2008 and 2011 respectively. From 2010 to 2011, he worked as a project trainee in Microgrids Global R&D, Mumbai, India. In 2012, he received the prestigious Microgrids Research Fellowship Award for pursuing PhD. From 2011 to 2017, he was a CGRF research scholar with the Department of Electrical Engineering, IIT Bombay. From September 2017 to September 2019, he worked as a postdoctoral research associate in Freedom Systems Center, NC State University, USA. From November 2019 to January 2022, he worked as a technical lead in L&T Technology Services, Bangalore, India. He joined Hitachi Energy Limited, Chennai, India in 2022, where he is currently working as an R&D engineer in e-mobility and power conversion solutions. I welcome Dr. Venkat N. Jakka to begin the session. Thank you, sir. Over to you, sir.
Yeah, thank you, sir, for the introduction. And so I just would like to share my slides. Just let me know, sir, whether you are able to see my
Sir, it is visible, sir.
Okay, thank you so much.
Sir, you can call me as a Karthik. I am a research scholar.
Okay. Hi, Karthik.
Thank you.
And
Thank you,
yeah, so good evening, everyone. And myself, Venkat, and right now I'm working as R&D senior engineer with Hitachi Energy Limited, where I'm mostly working with e-mobility and power conversion solutions. Mostly it is related to EV charging infrastructure. And yeah, it's my privilege to be a part of this online short-term course on power electronic converters, applications in microgrid and vehicular technology, as part of NAMPED and conducted by Electrical Engineering Department of NIT Rourkela. And thanks Karthik for reading my introduction. I don't think I need to go inform more about it. So yeah, so I'm going part of this session. I'm going to present topic on solid-state transformers for microgrid application. Before starting the talk, I just would like to give a small glimpse on it that I had worked as part of my PhD and a postdoctorate in some areas of solid-state transformers. But I was instructed that this course is basically targeted to graduate, undergraduate, and mostly PhD scholars and some industries. So by considering all the audience from starting and just giving an high-level introduction and the possible scenarios of application of solid-state transform, not in much higher or much lower technical, just it's a kind of high-level presentation, I can say. Yeah. So the key outline of my presentation is like introduction, solid-state transformer topologies, applications, and concluding remarks. So I like this cartoon which is shown in this figure. Basically, it's a small cartoon. It is taking the power from the ultimate god, the sun, where we everyone we treat like he's the ultimate resource of the energy, and we take the energy from the energy is being taken from the solar panel, and it is coming to a distribution box, and it is connected to one is a scooter and another is a small boat. Both are being charged here, and they can be utilized for you know, uh, for transit. At the same time, it is associated with a pole where you can use a street light. So it's a small, sustainable small microgrid, we can say, where the power is taken from the sun and it is being utilized for our modern requirements. Even though it is small, but there is a lot of technology involved in this, cartoon. Yeah. Coming to the smarter grid, the grid requirements is has to be smarter, and it is becoming loads also becoming too much non-linear from day to day. So power generation is almost there, but the utility or the kind of application of that power, electric power, is changing drastically from last 20 to 30 decades. There was a day where we are happy with our electric power. If it is giving light itself, it's more than enough for us. Later, we started using as a motor industrial application. Then it becomes essential for our entertainment purpose. Now even it is become necessary for talking or breathing. Everywhere we need electricity. Either it may be generated from grid, or it may be generated from solar renewable energies. But the thing is that we need a electric power. It may be cell, or it may be anything else, or it may be fuel cell generator system. So the loads, the kind of utility of electricity changed in a wide variation. So this is good one way, and another way it is also putting a lot of stress to the power grid operators. Different kind of loads are increasing with a high nonlinearity, and to mitigate and without impacting its supply across the globe, it is one of the most challenge for these days applications. At the same time, we are also running conventional most of the grids. There was days where we are completely relied on fossil fuel based electricity generation, and it had been become more than 22 decades, we can say, that people started realizing that we need to find alternate solutions where we can have the generating electricity generation from alternate resources like PV, wind, and wherever we can without using fossil fuel. It will be great impact for our upcoming future. So the demand for versatile energy management system capable of handling conventional and sustainable sources and distributed energy, all this for the transmission as well as the distribution system is increasing day by day. And with the addition to this, the data has to be taken from different utility perspective, maybe, or it may be from generating station perspective. Uh, it is really important to track on this so that the grid supplier will be able to provide an appropriate power to the different utilities. So the key objective of this smart grid is the smarter grid requirement is like service and easy distribution renewable sources into the existing grid plants. So already we have existing grid. If we can contribute some part of load requirement from micro generating systems or micro generating plants like maybe PV, or some cases it may be like wind, or it may be like fuel cell. If you are having some alternate where we can have it, it can better to integrate the local loads. And if we are having even more than that, we also this small generating system can also be a part of the big grid electricity supplier chain. So at the same time, we also have some storage devices where we can take store the energy if we are having more produced energy than what it is needed, and it can be used during the required amount of time. So here this diagram is showing different kind of activities we are using as part of power. There are some generating systems. There are some thermal, maybe generating systems, and there can be industries also. There can be nuclear power generation. We have the wind power generation systems, and we have transmission systems, and also we have renewable energy-based systems and storage devices. Also, we are going to have electric vehicle, which is to be charged from our home, and smart distributors and transmission system feeders. Everything is there, and all they are needs to be communicated to the system where we are having the tracking the information of loads as well as generating systems as well as transmission and distribution equipments of smart meters. So this is a kind of high level picture, the different way we need to generate, utilize as well as transmit. I mean, you can say it's a communication in cell phones. We are telling someone and someone is receiving, and similarly here someone is producing and someone is taking, but the media also we need to track it. So different ways of smart equipment are being utilized, as part of this coming versatile energy management systems. So this is a kind of the requirement or recent trend how we are looking into our power system from utility point of view, from generation point of view, and the smart application point of view. So many we are engineers, and mostly I'm thinking audience is also from engineering background. So I just limited the people who are working for this. There may be other streams also who might be contributing indirectly, like chemical engineers or who are deriving equations to generate electricity, or there may be some material science people, or there may be biomedical people also who might be contributing. But as it's electrical department, I mostly listed the names which are somewhat familiar with our department, this department. So many technological advancements which are mainly are focusing to meet these requirements are like information technology, communication systems, control system, power electronic and power systems, instrumentation and measurements. In different field, people are working to match these versatile requirements. So solid state transformer is one of the such technology to meet such requirements. It may be a part of combination of multiple of these factors, and it is trying to meet some of the requirements which are demanded by our modern power systems. The concept, the basic concept of solid state transformer is to meet some of these technical challenges which are coming or being required as part of this modern electrical systems. So before going to solid state transformers, it's a kind of transformer. Basically, we derived this from transformer. Transformer is well known to most of us. Like it is a kind of its structure is very well known, and it is a first subject what we are going through, and we are trying to understand when we are going for electrical engineering subjects. So that's ideally, if we see ideal transformer, it will have one core and two windings, or it can be multiple windings. For the sake of simplicity, I have shown here only two winding transformer, and somewhere the core where it is having here, and it is over the core it is having multiple windings, and energy is being transmitted from one winding to another winding to electromagnetic induction. So when we are talking about transformer, it has a wide kind of transformers we will come to see. There are transformers which are used in small scale electronic circuits, which can be rated for 3 volt, 6 volt, or even lower than that, and some which we can lift in our hand or our palm. And even there are some transformers which are rated for like hundreds of MVAs, which we may need to lift using cranes and very dedicated systems. So all everywhere it is a transformer, but it is meeting the requirements in different levels and different parts of our power conversion and transmission process. So the conventional transformer are relatively they are economical with respect to their work activities, and they are highly reliable and quite efficient. They are one of the most efficient devices in our electrical world. But some of the existing problems with the conventional transformers are like they are sensitive to harmonics. And for example, a transformer is designed for let us say 50 hertz, and if you are applying a higher frequency with the same rate, so then it can lead to issues. Or if you are decreasing the frequency, means highly it is sensitive. And there is also, if there is any change in line grid voltage, then it is also when we are change it is connected to heavy load, then there can be a possibility the voltage will reduce. I mean, it's directly replicating, just transmitting without doing any activity. If any load is increased, it will directly impact voltage of the grid without having any compensating part of it. And there is no inbuilt protection of it. And it is also some of the transformers which are basically oil immersed. They are also having some concerns related to environment. And when it is subjected to DC, it is have poor performance, or it can have huge damage for the system. At the same time, it doesn't have also any inbuilt power factor. If you are changing load, or if you are having loads, it will the current will directly replicate on the grid, and which may create a problem of power factor analysis. So these limitations may play a vital role when power quality is being considered. So the mainly the SST is a kind of the modification of the existing transformer with power electronic converter system along with high frequency transformer to meet some of these limitations. So coming to SST development, this concept is people are trying, or researchers and engineers are trying from quite a long time. But even though directly SST is not had any success, means sound success stories, but the concept is being utilized in different aspects. Even though they are not in solid state transfer, but the concept is being well utilized in various applications. So the first solid state transformer kind of activity has been filed patent by McMurray from GA 1970. And similarly, in 1980, a novel researcher proposed one AC-to-AC buck converter. Basically, in 1980, this GL Brooks named it as the solid-state transformers, even though it is not having any isolation. From that day onwards, this term has become very popular, and various people are using it. And in 1997, high-power AC-to-AC conversion was proposed. SRT means it doesn't have any DC link, which we are going to understand in coming. This is basically proposed by Prasad in GTNT. And in 1999, a new three-stage SST was introduced that we are going to see, like ST Sudof and from Garve. So this is three-stage SST is becoming more popular, and that is being used in many applications. So coming to SST topologies, there are various kinds of topologies are available, but out of that, I have broadly listed out, and I'm showing three different kind of SSTs. First is like AC-to-AC buck converter. It is proposed by G.L. Brooks, which is I said in novel here 1980. So in this case, what he did, he used multiple, just like buck converter, he used, this turn on turn off kind of activity, and he found on average, and that is being used depending on our, it's just like a DC to DC converter. Instead of DC to DC, it is best, just converting AC to AC part. And that is filtered, and filtered AC is being used as this one. So even though it doesn't have any transformer isolation, but it is named as one of the topology for SST. So this transformer, without any isolation, it is transmitting, its voltage levels. But the demerits are like that. These switches must be able to block the full voltage. If it is higher voltage, voltage conversion is needed, like high voltage to low voltage, which is rated for like 11 kV these days. Maybe we are getting, but if we look for IGBTs, it may be challenging now. So getting SSE these silicon-based switches may be challenging for such kind of applications. And it needs to conduct the full secondary current through the switches, which may be also one of the challenging part of it. And if we are adding multiple switches to block the voltage, then the control of the series switches also one of the challenging. And there is no isolation between the primary and secondary, and it is also doesn't have the capability with this direct topology to enhance the power factor. The second topology, if there are any questions, please interrupt and ask me, or it can be taken at the end also, that is fine. So the second one is AC to AC buck converter. One is done, and then second one is like power voltage conversion without having any DC link. So in this, what is there? There is a high voltage, lower normal conventional grid frequency AC is converted to high frequency AC as shown here, and that is being stepped up or stepped down using the high frequency transformer, and secondary is again converted back to AC using AC to AC power converter. So this uses isolation, and as we are using high frequency transformer, comparatively it will be have lower weight and size with respect to conventional transformer, and it also provide isolation, but there is no any first these storage elements in between this structure, so there is no power factor improvement in this topology as well. Coming to the third one is like three-stage SST, which is proposed by Sudo, and later various versions of it has been used by different researchers and industry people. So it has a structure like three power conversion stages. One is input, which is converting AC to DC, and another is isolated DC to DC converter, which is converting DC to DC, and the third stage is like output, which is converting DC to AC. So high voltage AC is converted to high voltage DC, or modular structure low voltage DCs, and the DC is converted to low voltage DC, and the DC again converted back to this HV set DC is converted to low voltage DC using isolated DC DC converter, and this low voltage DC is converted back to AC using the DC to AC converter, which is connected to load, or it can be like either way, high voltage AC to low voltage AC, or low voltage AC to high voltage AC. It can be also bidirectional as well. So here input part AC is a single conversion, and output also similar. They can be treated as like front end converters. And isolation stage is not a single converter system. It is having DC to AC, a high frequency transformer, and another power conversion system like AC to DC. This isolated stage itself is again two power converters along with one transformer. Yeah. Ideally, we tell it one converter only, like resonant converters, dual active bridge converters, or some isolated full bridge isolated converters. Different several kind of converters can be used depending on the type of converter you are bringing. They can name with respect to that. So the key merits of this kind of structure is it is reducing size due to high frequency transformer, and it is also having power factor improvement is possible because you are adding the storage capacitors, so they can utilize inject and take reactive power requirement support to compensate additional power factor adjustment. And as multi-level converter systems can be adapted for this application to meet high voltage application with the limited rating semiconductor devices. The key demerits are like it is high cost, and as we are adding number of power converters, comparatively lower efficiency. And this is most popular topology being adapted in several applications. So these all are like these are just each stage what they are doing, and like input and output are can be used for power factor compensation, and just to meet the load requirement or source requirement. And this is to step up or step down the voltage levels, this isolation part, and also to provide isolation. So it is made the different part of it, which is already being discussed. And one of the, there are several, and there is a key difference between transformer and solid state transformer. So transformer has a fixed structure, like it has one core, and over the core multiple windings are wound, and depending on the number of windings we name it as multi-winding, two winding, three winding transformer. But here solid state transformer doesn't have any fixed steps, structure. Right now we have seen three different kind of approaches to achieve SSTs. Even thousands of researchers or papers you can find. Each SST has a different structure. They may have some different kind of AC to DC converter, or they may have different DC to DC, or they may have DC to AC, or some are instead of connecting in series, they are connecting on DC side itself in parallel. So it's a kind of puzzle. As for your application requirement, you can configure and you can use it. Only thing is that there are some high frequency transformers along with power converter systems which is meeting your requirement. So that is a huge topic. Just let us pick one out of it, and I am discussing here. So the primary side, it is a cascade edge pitch converter, which can be utilized for a high voltage side, and it has multiple DC links, and the DC links are stepped down by using this dual active bridge. And dual active bridge secondaries, all secondaries are connected to a single DC, and the DC is converted back to low voltage AC using DC to AC converter. Here I have shown edge bridge kind of system. Depending on the requirement, you can use multiple DC to AC converters. So applications. I hope is there any questions in this part, topologies and its SSTs? So let us go for please.
Sir, may I know, can we call like this solid state transformer? It's like a dual active bridge. I mean, how to understand these two terms?
Dual active bridge itself is a dual active bridge. If you are using dual active bridge along with dual active bridge, I'm just giving one example. If you see the dual active bridge, you are using dual active bridge one, H bridge DC to AC part, which is basically known as inverter. Secondary side, if you see, you are converting again H bridge using AC to DC. It is basically a rectifier. Can I call dual active bridge as an inverter or rectifier? It is tough to say like that. If you use this dual active bridge along with this AC to DC part, or along with something, you are adding some more additional converter system, and then you can say SST. I hope I am clear. I could able to answer.
Yes, okay.
Because if you break it, you will get multiple. We are also using transform. Can we take dual active bridge as a transformer? It is tough to say, but as an overall combination, we are saying one name. That's it.
Yes. Thank you, sir.
Thank you. Any other questions? I could not that I can go for the next part. So I have picked some of applications. There may be even more out of it, just to narrow down our talk. And as an initial stage, I found some applications like microgrid system and renewable energy systems like photovoltaic wind power and traction transformer and electric vehicle charging stations. So just I would like to remind this SST, three-stage SST, if you see, right, it has a different stages in it, like high voltage AC, high voltage DC, low voltage DC, and the low voltage AC. So it has a wider range of choices for DC as well as AC. So you can integrate a wide variety of levels of DC and AC voltages as well as sources as well as loads. If you make them as a common bus, then you will have a freedom to integrate multiple wide variation of different sources and loads. This is one of the key advantages which will help to extend this concept for various applications. Application of SST, as I said, let us go for first. These are these are almost I have I just discussed. So in microgrid basically it is an excellent utilization of distributed renewable energy resources and distributed energy storage devices because it has wide range of DC and AC systems. So it will have more applications. Means you can have the flexibility to integrate high voltage storage systems and sources as well and low voltage as well. And it has the features to inbuilt power factor control and fast isolation under fault condition due to control switching devices. If there is any problem or any either way, it may be from loads or source or any concept, we can have stop it means using the control switches, and we can have use both AC and DC. So my voice is clear that I just
Yes, your voice is clear, sir, but simultaneously we are able to see some kind of noise.
okay.
It's clear, sir. Your voice is clear.
Okay. Yeah. Just I thought there may be some in between. I felt some disturbance. That's why I was just asking.
I think it is coming from your end, sir.
Okay. Yeah, I think from my side, some neighbors maybe. Okay, thanks. So this before going to SST-based microgrid, let us have one AC microgrid. In AC microgrid, basically the common bus system, which is mainly the AC, where you have loads and both loads you can have AC loads and DC loads at the same time. You can have sources also and storage systems from both DC or if it is I don't think any we have wind it may be AC, otherwise it is like DC kind of systems. In this picture I have only shown the DC source and energy storage backup, and it can be connected to grid, and that grid is connected to the dotted line basically source AC microgrid system. And microgrid system is connected to grid via transformer, and the AC bus is directly connected to load, and the DC sources what you are having, you are connecting to the AC bus common bus bar system through DC to DC converter and then DC to AC. And similarly this sources also you are connecting DC to DC then DC to AC part. And if you have any disputes, you can use AC to DC and you are connected to. So this is a kind of AC microgrid structure. Similarly, if you go for DC microgrid, you will have DC bus and you will connect that DC bus to both DC loads, AC loads, DC source, and if there is an AC there also. And mostly microgrid systems we expect, so lower, and if it is a kind of wind or something, it is a kind of little big grid. Otherwise, installation cost also may be like that. So DC microgrid, it is there when you are integrating to grid. Along with transformer, you need first to convert back to DC to AC, then AC to whatever grid voltage you need to convert into DC. And you are connecting to DC bus, and you are connecting to DC load directly. And if you have AC loads, you are using DC to AC, and if you have any like sources, mostly you are using DC DC converter. If you see with respect to previous AC microgrid to DC microgrid, comparatively lesser number of power conversion systems are needed DC part. So these are both AC and DC microgrids. Now let us see SST based integrated microgrid systems. As SST has both AC and DC busbar systems within it, so you can directly use AC of it to AC loads, and DC bus can be directly used to DC load and to integrate the storage backup as well as your load systems. So here even you are reducing more number of power converters. There are converters in SST, but if you come out of SST, then for distributed grid where you are once you got the common bus, if you would like to add or install some additional loads or sources, during that time you don't need to add more power converters. So that is one of the advantage of using SST based microgrids. And for traction application, basically in traction systems also, this weight also matters for some traction like railways and others. It's mainly for passenger trains. It some traction transformers like for these trains which are meant for taking coal or minings. So there even you are having added weight may be advantageous, but passenger trains, if you are able to reduce the engine weight, then it may be more advantageous. And if you are distributing the weight across the train, even it will be more efficient for the motor system. So one of the key application of solid transformer is for tractions, and it is like high voltage to low voltage system. So the primary side, it is connected with modular structured inverter, and that is converted to isolated DC-DC part, and the DC2 is connected to AC, and all connected in parallel to connect the motor. So it reduces weight and height and increases the efficiency and reduces line filtering. So yeah, as you are adding power compensation itself within the transformer itself, so we can the filter requirement will be it will be optimal. It is one of the traction transformer installed by ABB. I think it's in 2010 or nearby that era. In Geneva, they successfully commissioned and tested. And this is like solar application. It is also a kind of microgrid, small microgrid, where you are having DC to DC. So instead of AC to DC, we are using DC to DC. Then you are using this isolated dual active bridge. I mean, this dual active bridge or DC DC. And if you want to inbuilt MPPT within this, I mean, it is a DC to DC, DC to AC, and here like AC to AC. Here we are getting high frequency AC. And high frequency AC is converted to low frequency AC, and we are connecting. So this is a kind of one of the application. And this is for wind, where you are having one AC to DC part, and then dual active bridge, and all the dual actives, multiple different winds are connected in series to get high voltage, and that high voltage is being transmitted through DC cable to the onshore, and there you are again converting back to DC to AC and integrated to loads or grid. And another is like for electric charging part. So you can connect grid high voltage to in the modular, and all the DC side connected to low voltage parallel, and that low voltage is being used for connecting different vehicles or charging systems. So here it is shown like one is rectifier DC dual active bridge, and connected to a common DC bus. It is also a kind of, you can see, DC microgrid where PV is also integrated there, and their DC loads are connected. And you can see here storage systems like you have the PV and you don't have any cars, you can store it, and you can keep it and connect to the different charging equipment. So this is one of the application. I mean, the way in which you would like to configure, it's a kind of lot of converters, sources, loads, everything is there as per your requirement, how you are picking the independent equipments and assembling. The main thing is that you are supposed to meet your requirement. You are assembling, but if you are not meeting your requirement, there is no use. You take it, it's a kind of everything available, take the existing technology and assemble and provide a solution which will meet your requirement in an optimal way, so that you are providing a solution, but it is taking like for 1 rupee you are spending 100 rupees, then there is no one will willing to do that. And similarly, at a period of time, if you are able to compensate, it's okay. It's people will accept. Anyway, this technology is good. But there are trade-offs. One is technology, and one is a requirement. One is maybe some technology is good and but not efficient to implement now. But it may at some point of time it will be useful. It is also possible. So there is a trade-off in different angles. Based on that, we need to select our concept. So this is a smart microgrid. This is having different power converters, and basically as each stage we have some converter system, and each converter system needs to be operated with some controller. So controller is a kind of intelligent activity. So each controller have the capacity to communicate with other controller. So there is a higher visibility to take the information and communicate with if there is any management system or central processing unit where or you are storing the data or information of how your power consuming at different times. So all these possibilities are possible by adding the smart features. These are some of the comparisons I have shown here. So why even there are many more out there, but I have selected few which are most successful. Power rating available for SSTs are like up to 1.2 MVA, which I have shown the traction transformer, and they are being used in smart grid, DC charging stations, substation tractions, and even efficiency. We can see the different structures have different efficiency, like starting from 92 to 94%, and they have whichever companies they made and different features, whether they are providing or not. Coming to advantages and limitations, the advantage is basically like it is improving power quality and DC and alternating frequency service options. One of the applications I worked in Freedom System Center is like even if two grids are there and they are not synchronized, then also we don't have any problem with SST to integrate it. Yeah, that is one of the advantages, and integration with system monitoring and advanced distributions also there, and it is reducing weight and size, and it is also eliminating hazardous liquids. Limitation is like that it has multiple power conversion stages, which can lower overall efficiency, and it is using basically storage capacitors. Usually we treat like capacitors have less lifetime as compared to inductors. So that is one of the challenges. If you are getting good capacitors and storage, even it will be more really reliable and robust. And it looks like as we are adding too many semiconductors and storage devices, we can say this transformer lifetime also one of the challenging part of it. Yeah. So challenges and opportunities like we are able to improving in efficiency and as much as we can decrease the power consumption stages and appropriate control algorithms so that the losses in different power converters can be minimized, and if you are able to propose some modulation techniques to reducing switching losses, and if there is any way to reduce the cost, these are the challenges which we can do. And it has wider opportunities like hybrid electric vehicles, electric vehicle charging systems, ships and submarines, traction locomotives, microgrid, and distribution systems. Thank you for all for attending this talk. If you have any questions, we can discuss. Hello. Hello. Am I audible?
Any queries from your end?
Am I audible? I think I missed.
Sir, you're audible.
Yes, sir. You're audible. Yes.
Okay. If there are any questions, we can take it.
Sir, apart from technical, I would like to know some things about it. Sir, as a research scholar, I would like to know that that your industry like Hitachi Energy is offering any internships for PhD scholars, sir?
Usually they offer, and they takes, I think, the process I'm not exactly sure, but they take some internships which takes 10 months to, like, they spend some time here, and I think 4 months to 10 months. But I think professor from your university, yeah, I think they are taking. I have seen some interns, but you can think Indrajit also might be having aware of.
Yes, sir. That is also there.
Yeah, sure.
Okay, sir. In this record,
Usually people come and do the internships. I had also done when I was in masters. Yeah, most of the R&D centers it will be there, but if they have requirements, they will contact, or people can directly. Sometimes in portals, the students applies for internships, and HR people will communicate to the relevant R&D teams, and they can also. There are different ways of getting.
So can I have your contact details to know further? Like,
I think you can contact Indrajit. He can help in that. He's we are in touch with that.
okay, sir. Thanks.
Thank you.
I think there are no. I think there are no queries from participants, sir.
Okay. Thank you then.
I think.
Excuse me, sir.
Yeah, please, madam.
Yeah, actually, I have a doubt related to the construction of this SST. Is it
Yes.
much different from the conventional type, and how the protection we are providing?
Yeah. So one of the aspect is like SST is it is not nominal and only one winding and two winding and core. So it has a lot of constraints related to its protection part. So one thing, whatever conventional protections are needed, everything we have to adapt here as well, like surge protection, like our voltage, our current, and short circuit. All these protections at a system level, we have to provide from the grid point of view, where we are in a point of common coupling or integrating. At the same time, internally also you need to have a lot of protection schemes, like I will take some slides here. Sorry. So where it is? Yeah. Here, this is having a lot of capacitors, and primary side it is not some, but inductors are there. And some issues like when there is no charge across your DC link capacitor, you are directly connected to grid. It will see like huge interest will come, and that can lead to damage of the switching devices. So what you maybe this charging, either you have to provide the charging before utilizing into them, or you will use high resistance path at the primary side before it comes to charging. Then once it is charged, you will bypass those path and you will directly connect to your supply. And at the same time, there even if you are stopping, there can be charge store across the capacitor. You will see the voltage, and you need to discharge those. So as part of one of my work in Freedom, I have made protection design considerations for SSTs, where I made it three different ways. One is like conventional protection. Second is this converter level protection from the using hardware setup, and the third one is software protection. So even when it comes to conventional protections, you are using fuses and surge arresters and pre-charging and charging arrangements. All this will come as part of conventional protection systems. And when it comes to power converter protection point of view, even you will have a protection feature from gate driver circuit for the device. If your device gets short circuited and it detects any such scenario, gate driver itself will turn off all the switching signals. This kind of activities, as part of converter system protection, level protection. And when it comes to stop software level protection, there is an emergency button. If you are pressing, then it will take and it will stop all the gate pulses. Or if you find any high current, high voltage, this kind of logics you will implement as part of software. I hope I could able to answer your question, madam, or anything else.
Yes, thank you, sir.
Okay, sir, good evening, sir.
Yeah, good evening.
Compared to conventional transformers, the size of this SST transformers are large.
It is not true, because this figure looks, bigger. But if you see one, I say 10 kVA 5 kilo 50 hertz transformer and 10 kVA 10 kVA 20 kilohertz or 50 kilohertz transformer, right? There will be very huge difference you can find in the weight and volume. And coming to power converters, if you use power converters, something like big heat sinks which are overrated, then it will be big. If you properly assemble the power devices, press packs, and this heat sink properly planned, we are using air cooled heat sinks, it looks like big. If you are using some liquid cooled heat sink, right, its space will be much more lower than that. So it is depends on how we are going to implement and assemble the overall system. Otherwise it will be very big. Just like you can see old days, this BJT based amplifiers and SMPS what you are using in your computer, you can lift it with hand in SMPS, even though it is 500 watt or like 750 watt. It's same with old days power systems. If you, it is a kind of SMPS only, nothing else. It is scaled version of SMPS. So that replicated in high power also with added protection features. This matters how we are going to assemble and implement.
Okay, sir. Thank you.
Yeah. See, one way, like if you are using one device which is rated for 10 kV, then one device is enough. Okay. If you are going with 650 volt devices and 10 devices we are adding, then you cannot say it will compete. You need to select the right choice of components to be compete with the existing system. Yes. Hope we are.
Any queries? Sir, I think there are no more queries.
Okay. Thank you,
sir. Thank you for joining with us and sharing your knowledge. Thank you so much, sir.
Thank you so much.
Thank you, sir.
Thank you
for delivering your very informative and beautiful presentation to us. Thank you, sir.
Thank you so much. And hope everyone have a nice day.